Hello, and welcome to my course on C. I'm going to make this a series, and I'm going to call it the C language taught my way. So I said in a little video I did not so long ago that strlen is a function which is very much overused by people who have a very basic knowledge of C, and this prompted me to say that I was thinking of making my own C tutorial series. And now I've finally decided that I'm going to actually live up to my goal and actually try and teach C. So it goes without saying that C is a programming language, and that I use it, and I really like it. I think that C is a fantastic language, and that it combines just enough of modern programming and just enough of old programming to make it a traditionalist language, in that you can do things the old way, which I think is the right way. And in fact, C is old enough that you can still learn it out of a book. Or in fact, I did learn it out of a book. Now, this isn't actually my copy of the C programming language. My copy is a lot cleaner than this. But my copy of the C programming language does have a lot of dog ears and actually has writing in it, because I used this to teach myself C inside and out. And that's my goal to do today, because back when this language was created in 1972, you couldn't just learn a programming language off the internet like you're doing now with this video. Instead, you had to actually get a book, and you had to read through and absorb the information. And admittedly, that's hard. And so I want to try and make this process easy. And some of my motivation for doing this will be clear later on. But for the moment, I think it should go without saying that I think it's an important thing to learn C. I think most programmers should do this. However, C is a Swiss Army knife of a language, if this makes any sense to you. If you use it correctly, then you'll get outstanding results. If you don't, well, you get a program that's either not going to work at all, will barely work, or will actually damage your system if you're not careful. And unfortunately, programs that are written like this often come as a result of just really bad teaching, and so you get terrible results. And so the language actually needs to be taught properly, and this is extremely important. And unfortunately, this is often not the case. I've prepared a modest example here, and this is from tutorialspoint.com. There is so much wrong with this example that I can't even get started. First of all, you're pushing a char buffer onto the stack, you're putting 100 maximum values onto it, and then doing an unbounded get, reading as many characters as we want in. This will cause a stack overflow, which is a security issue, and at best will crash your program, at worst will cause a severe security vulnerability. Then after this, they misunderstand the point of printf, by printfing a static string, and then calling puts on a string that could have been printed using printf. This is the whole point of printf existing. And yet, people who are attempting to learn C and attempting to learn how input and output can be done efficiently and well, and with elegance, are being taught that this is the correct way that they should be doing it. This is bad. And even in the note here, they admit that it's bad. But then all they do is give you a link to a POSIX manual for fgets, I think missing the entire point. There are so many better ways of doing this, and they've completely missed them. And this is a prime example of terrible C programming. And so I'm going to do it myself, because when you can't rely on anyone else to do something for you, you just have to take on the mantle yourself and just do it. So what are my aims? The aim is to attempt to teach C with depth. We're going to go to the very depths of the language, learn the internals of what C is doing, and we're going to properly learn exactly what the C compiler does with your code as it's going through. In the immortal words of Linus Torvalds, when you program in C, you know what the resulting machine code will look like, and that's important to me. It's important to me as well, not just to Linus, because I think that's what makes C such a perfect blend of high and low-level programming, especially given the time frame that it was created in. I also want to do as much breadth as possible. For each topic, we're going to learn the insides and outs of how it's useful, how it works, and what exactly C is doing under the hood. Because, and this is our first golden rule of C to remember, C is just a tool for generating machine code, and that will make a bit more sense in a moment. I want to give insight about inside knowledge and the language. We want to know exactly how linking works, exactly how compiling works, exactly how the AST is constructed, how recursive descent parsing obtains an AST. We're going to talk about exactly how the C language is a product of all of that which came before it, and why it was the base upon everything that's come since it. And we're going to teach C through implicit knowledge from the underlying hardware. C is a good low-level language, and so in order to understand it, you first need to properly understand the underlying hardware of the computer. And so to understand C, you need to get under the hood. In order to understand C, you first need to understand computers. So, we're going to get started with this just quickly as part of our introduction today, because we need to truly understand computers before we're able to continue. So this here is a simple diagram of a CPU, and it might look complicated, but really this is very simple. A CPU is just a circuit on your computer which receives instructions and then does some command. It's basically something that receives a long script of things that it has to follow, kind of like the one that I'm reading now, and this is a long list of things that it's told to do. And these are stored in its main memory here. Main memory is RAM. So, the processor takes in instructions, it executes the instruction, having decoded it, and then it stores the output somewhere. So I've actually prepared an example here of something that we're going to have a look at to see exactly what these instructions look like. So, this is what machine instructions look like. And so what we can see is we have a memory address here, we'll talk more about memory addresses in a moment, and then we have the processor instruction here. So what you can see is there's a verb, and then there are operands. This is called an operation, and these are called operands. And so what the processor does is it starts at this instruction, it does it, and it goes on to the next one. Does this, goes on to the next one. Goes on to the next one, and it continues doing this until it reaches something that modifies where it goes to. For instance, call Q. Call moves this number to some different location. In this case, it moves it to the number after the call Q. And so these are generally quite self-explanatory. Move Q will move a quad word between RDX and R9. These are two registers. We'll talk about this in a moment. But mov, move, pretty self-explanatory. We can see down here there's an add B, which is add byte, or add. You can see call Q calls a function. LEA is load effective address. Sub is subtract, so we're subtracting 10 from the stack pointer. And so these instructions are very simple as they need to be implemented in hardware, but they're also very difficult to program with, and they're also very repetitive. In this case here, this subtracting 10, when we saw a minute ago the tutorials point example where they created the char buffer, that would be implemented as subtracting a 10, for instance, but multiplied by 100. And C will do this implicitly for us. You don't need to know this. But what you do need to know is that this is what C is doing in the background. And the reason C is doing this is because C is just a tool for generating this machine code. And this is what is stored inside of a binary file when it's loaded. This is what the processor sees. It sees a lot of binary, and it decodes internally inside the processor. It decodes to this here. It decodes to these instructions that tell it exactly what to do. And so it moves through them in a sequence, calling each one. Okay, so that's how the CPU receives instructions and knows what it needs to do. But how does it actually operate on anything? How do things work? How does it receive data? Well, the first important thing that a CPU has on it is a register, and these are very small, very fast, and very powerful little pieces of memory. It's like the short-term memory of a computer. Now, or I should say it's a probably short-term memory of a computer. It's the data which it's currently working on. And so you have lots of these registers available, and C will automatically manage them for you. You have a limited number, however, and they are of a limited size. So when you need to store larger things, like images for instance, you need to store them in main memory. Just for context, registers in 64-bit systems, they're 64 bits wide. That's what a 64-bit CPU means. That's only 8 bytes. That's not even large enough to store 1 pixel of a modern day image. So we need main memory. And this, if you've ever done anything with computers, is your RAM. The way that RAM works is I'll explain in a moment, but we store all of our data in RAM, and, crucially as well, we store these instructions. These instructions will be located in RAM, and they will be located at a certain address, as we can see here. Now, these that we can see here are the registers, and you can see that they all start out at 0, apart from this here, the instruction pointer. The instruction pointer is the memory address of the current instruction. Remember, these are all stored in memory, and that everything in memory has an address to show its location. This is just the address of the current instruction. You can see that all the other ones start out at 0, and so these can be modified at will by the program as we're running. Okay, so that's the basics of a CPU. But now we were talking about memory, so how does memory work? Well, this is a simplified diagram of what memory might look like. Memory is just a big, long list of blocks, all of which we're able to write to, in theory, obviously. And so these blocks are called bytes. And these bytes are the fundamental unit, apart from bits, which are the things inside of a byte, but bytes are the fundamental unit of computer science. And so our memory space is broken up into bytes. And each one memory address, each 1, as we go up in 1, you go from 0x1 to 0x2, is 1 byte. And so there's 1 byte in between these. So we can imagine each of these blocks here is 1 byte. And so what this means is we can store lots of different data in RAM, but we address it based on the byte address. So 0x0 in theory will be the first byte of your RAM. It will be the very first piece of memory that your computer is able to access. And so the CPU issues the memory address that you want to get to the RAM, and the RAM responds with the data that's at that certain address. Now, when your C program is running, there's something called virtual memory that is set up by the operating system to make sure that you can't actually access the RAM that other programs are using. And so all you can actually see is the RAM that your program is allowed to use. And even then, there's still RAM that you're not allowed to use because, for instance, it might contain this code here. If you do use it, you'll either crash or change the code of your program, which will definitely have bad consequences, I can promise you. And so C allows you direct access to this through pointers. Remember when we said that we have an instruction pointer? That's what the IP stands for. Whenever you see pointers in C, you should always remember that this is just a number that points to a location in RAM. It's just the number of the block that we're referring to. And so our RAM is broken up all into these little blocks, and these all have a number to show their address, just like houses might have addresses. So, as we were saying before, C is just a tool for generating machine code. And so this, as an explanation, is to sometimes why, when you're programming in C, you might have a little moment of annoyance and go, why can't C just do this for me? This is so, this is manual work, essentially. Why can't C do this for me? Because C is an indifferent tool. Under the hood, it's generating all of this for you. There's an enormous amount of work still involved that the C language is doing for you. But because C is not only slightly older, but also is giving you a large amount of control, the C programming language doesn't include certain features that people think should be standardized. And so these features were then further implemented in C for higher level programming languages. So this, hopefully, we should remember this then as golden rule number 1. C is just a tool to generate machine code. And so this is what C generates after it's compiled your program, it's called. So this is what I was talking about with virtual memory a minute ago. We don't really need to know this, but virtual memory essentially makes it so that your program has its own little block of memory that only it can see. So at this point we might be thinking, okay, this all sounds a bit complicated. Why do I need to know this? Why do you need to know this and do all of this complicated printfing stuff when instead I can just type Python in my console and type print hello world? Why? Well, I'll give you a very simple answer. Because we have to. We have to do this. There's no other choice for us, honestly. It's our generation's turn as computer scientists to take on the mantle of having to look after all of the code that our ancestors wrote. Because everything around us is running C. Everything around us is powered, at least in part, by something that's touched by C, or something that is based on having C code compiled into it. The operating system that you're running currently. If it's Windows, the kernel's written in C, the rest in C++. If it's Linux, it's wrote entirely in C, almost. If it's macOS, ditto. Almost all of the software that we use in the modern day is at least at some part touched by a C compiler. Even all of these soy programs that people write nowadays in programming languages like Node.js. What do you think Node.js is written in? It's written in C, of course. What do we think that Python's written in? Well, it's written in C. CPython is the repository name. All of the software that you're running is running C. And so you can get away with it. You can keep writing software in your high-level programming languages, but eventually you'll find a problem, or you'll need a feature, or you'll need to innovate in some way, and you'll wish one day that you'd learnt C. All of the first-generation computer scientists, the pioneers of the field, all programmed in C, because it was the best tool that they had available at the time, but also because of the control it gives to you. And so our society, with a lack of knowledge of C, begins to die out. The Holy Roman Empire began to collapse as soon as people forgot the skills that their ancestors had had. And as soon as people forget C, our computers are doomed. Think about it. The first generation of computer scientists are either slowly dying or are already long into retirement. The Linux kernel is written entirely in C, so somebody needs to maintain it. Who's it going to be? A lot of Google software is written in C. Just ask Rob Pike. This is a picture of Dennis Ritchie, who was one of the creators of Unix, and he has now died, sadly, or died, I think, in 2011. This is Ken Thompson receiving an award for computing, and he's now retired. This is Brian Kernighan, one of the authors of the C programming language, who's now retired. And this is Linus Torvalds, and he hasn't retired, although he is a middle-aged man with, I think, 2 children, and so he's going to be getting on, and he's going to be retiring one day. And so is Greg Kroah-Hartman and Andrew Morton and all of the people who maintain the Linux kernel currently. And that's written entirely in C and in x86 assembler, for instance. And so, one day, somebody's going to have to do the job that these guys are doing. And somebody, therefore, is going to have to know C. Somebody needs to know the tools that our computing ancestors used, lest our society completely fail. And so we have to take on the mantle that our older generation has done, and just learn this language. It's not even a bad language. I very much like it. I think it's a fantastic tool, and I think that Linus's reasons for liking it are very similar to mine. And yet in the modern day, people would much rather write programs in inefficient, high-level programming languages that are unsuitable for their purpose, and shy away from computing at a low level. I'd even go as far as to say that a large part of programming the modern day is really scripting rather than actually programming, as it's not actually programming the machine, it's programming another program that programs yet another program. Like, think about TypeScript. TypeScript is programming for writing another program that essentially tells the JavaScript program the JavaScript interpreter, which is another program, what to do. It's a program that programs a program that programs a program. This is as high level as it can get. And we're starting to forget our roots. And so now it's our turn. So, I'm going to sum up here, and there's some corrupted text in my text editor for some reason, but I'm going to first sum up essentially what this series is going to do. So you're going to need a compiler compatible with C99. I'm going to use the TinyC compiler, TCC. It's free for download. It's licensed under GPL if you care about that. You can get it on Arch with pacman-s TCC. It's a really small program and it's really fast. Your hardware will support it. And basically any compiler that's been made after like 2004 is going to support C99. There aren't that many extensions that we're going to need. In fact, there's probably going to be 0 that are absolutely mandatory. You're going to need a basic editor. I'm going to be using NeoVim, but there are plenty of good text editors out there. You can even follow along in Notepad if you want to, but Notepad++ is pretty good on Windows. I'm going to caution against using Visual Studio as it introduces certain ways of thinking that are not very good for C programming. And I should warn as well that you're going to need a basic computer knowledge and preferably another programming language, because this is not a beginner's tutorial. At least not beginners to programming, this is. You can be a beginner to C, that's perfectly fine. I can convert you from the cult of JavaScript if need be. But this is not for beginners to computer science. Don't get scared off by trying to learn advanced stuff before you know the basics. If you're just learning computer science, at least try writing in Python or Go or something like that first. So, as such, given that this is not a beginner's tutorial, depth is a key aim. We want to go as deep into the subject as we possibly can. So, we're setting off on a journey today in this series. We're setting off on a journey into the future of you becoming a C programmer. And so this is just me attempting to share what I know with other people. I'm going to attempt to keep the knowledge modest, despite how deep we're going to go into it, because this is simply my knowledge, and so I can never claim for a moment that I know everything there is to know, but hopefully I know just about enough to pass on the key knowledge that's needed for people who want to get into the field. So the last thing I should probably say is very good luck. Good luck with your future endeavours, and good luck with not going insane when you see a screen like this in the future, because we're going to be looking at it quite a lot. So, good luck, and see you soon.